And today I wanted to talk about a few things that are related to this. So I already mentioned metrics here. So let's talk about why choosing the most common metric is not obviously the best approach in every situation. So if we talk about metrics, this is something that we should really think about. So what is a metric? A metric is basically what we're currently considering the key to a trustworthy performance assessment. But what we see here is we see the weight of two people, which basically tells us nothing about how these people look. If we just say, okay, we have 100 kilograms and have a look at these two guys here, it doesn't really say anything about the look or the health or anything of that person. And I brought a few examples here. Here we go. So an example so I work in healthcare, so I have a few healthcare examples, but this also relates to many other problems. But something that we see very often, many people work on this, is brain tumor segmentation. So here we see an MRI of a brain, we see on the left a reference from a doctor, and we see a prediction. And in blue here, you see the outline basically of the brain tumor. And if we compare the reference from the doctor and the prediction of an algorithm, we would just from a first look say, okay, this looks really good. So the model did a really good job in segmenting this brain tumor. And if we look at the metrics here, this is the most commonly used metric for this kind of problem. 94% performance sounds really good. And this is an algorithm, this is an example, which is considered to have expert performance. However, it's not always as simple as that. In medicine, we often have 3D images. So if we look at this very same patient from the 3D image, just a different slice, we would see that this algorithm is not as good as we thought, because here we see that it misses this tiny lesion here, which is very important from a clinical perspective. This tiny lesion is much more important than this big tumor here, because this gives us some insights about metastasis, etc., and if the tumor has been cured. So this is what is interesting from a clinical perspective. And this algorithm is missing this tiny lesion, which could be really dramatic for the patient health, because if we consider the algorithm is good, but it misses the tiny lesion, we will tell the patient everything is fine after the big tumor is gone. And yeah, you could imagine how this could go out. So this metric is a very bad proxy of our real clinical goal. And we would need something like percentage of missed lesion or whatever in this regard to really reflect what we want clinically. But the problem is, it is not always straightforward to find the good metrics, because if we think about it, what kind of metrics and measures we have for performance assessment, there are many, many out there. And some of them, I just put a few here, may sound familiar, some of them may sound unfamiliar, and all of them have been introduced at some point in the last few years. But the question is, does it make sense to use them all in our daily lives? All of them have pros and cons, and it's really not straightforward to know about all their pros and cons. So another example here, if we think of sports, which is quite straightforward to us. If we think of Olympics or we have a marathon, it's quite straightforward for us to say who is the best in this situation, right? Because we measure basically the time for each runner, and the one with the shortest time is the winner, or the one who is the first on the finish line. So that's a pretty straightforward metric for us, and no one really questions that it makes sense to use that metric for defining the winner. But if I would tell you, let's use a different metric, let's use, for example, the shoe size of each runner, we would all say, okay, that doesn't make any sense. But this is the thing that we also need to consider when we validate our AI algorithms. We need to consider what's our actual clinical goal in order to measure success, or what is the goal if we want to have satellite images and we want to segment something from Earth or from matter. So we always need to keep in mind what is our goal in the end. So we went a bit into detail in this regard. So we had a look at how people select metrics. So what you see here are a few quotes from people who have organized competitions. And when we have the design of these competitions, we implemented a question where we asked people to justify why they used a specific metric. And these are things that we see very, very often. So justifications like, well, this is the standard metric for this and that problem. And this is a widely used metric. This is the most common used metric for XYZ. And this indicates that we are often using metrics because they're popular and not necessarily because they're meaningful for our application at hand. And if we look at numbers, this is also reflected. So here you see the frequency of metrics used in classification competitions. And here we see the same trend. There are some metrics, like at the top here, accuracy, area under curve, which are much, much more frequently used compared to other metrics, which may be more relevant for certain problems. And this may not be necessarily a bad thing. I am not saying that popular metrics are necessarily bad, but we should always think about if it makes sense to use that metric. So for example, accuracy here is the one that is used most often in classification challenges. So if we look into that metric, we will quite quickly see that this comes with a very prominent pitfall that you potentially have also heard about. So let's assume we have a binary classification problem. So you see, I'm from healthcare, so I like to use healthcare examples, but this relates to any other problem. So let's say we have a classification, we have a patient, and we want to say the patient has cancer or there's no cancer. Let's say we have a very imbalanced data set, like you see here. So most of the patients are healthy and only a few of them have cancer. We train an algorithm, we use the performance assessment, and we get an accuracy of 97%. And this is, again, a great score. But before you directly go to publish these results, we should think about this problem of class imbalance. Because what our algorithm is doing, it will always, in this situation, predict that someone is healthy. So it basically says, independent of what happens, I'm always saying this patient is healthy, has no cancer. And in most of the cases, this will be true. And therefore, the accuracy will be 97%, which is, of course, completely wrong. And we shouldn't use that algorithm in practice. But the reality is, in medicine, for example, these class imbalance problems are basically the everyday situation that we have to deal with. Class imbalance is a real thing. For example, if we think of disease prevalences, they're often very, very low. So this is the situation that we just face daily. And we should think about those things because there are metrics that can handle class imbalance. For example, balanced accuracy is a metric that can compensate this problem. And there are many other pitfalls for the popular metrics. So segmentation, for example, is a problem that many of us deal with. So if we think of a segmentation problem and something like this here, and we want to basically segment here the people and the motorcycles, we often want a segmentation where we have accurate boundaries. But if we look at these kind of random predictions that we see here, we would probably agree that not all of them are of the same quality in terms of boundary accuracy. So if we think of prediction 4, this looks pretty good. Prediction 3 is a bit random. Obviously, this is a handmade example, but still, we would definitely agree that this one is better than this, or prediction 2, or prediction 1, where part of the people are missing. But if we use the most commonly used segmentation metric, this metric will tell us that all of those 4 predictions have the same quality, which is obviously not the case because we as humans know that. But this is the same story. We have to know what are the things that we care about. In this case, it would be, for example, boundary accuracy. And therefore, we need to choose metrics that are appropriate to measure this. And I could go on with these examples for quite a while, but I don't want to bore you too much. But if you're interested in those, we have 2 papers where you can find many of those pitfalls of metrics. And specifically looking at the bottom one, this is a dynamic preprint. So if you're interested in adding more pitfalls that we may have missed, please let me know. We're always happy to extend it. But what I want to say is there are many, many problems of metrics, and it's really not straightforward to know all of them. And it's not that I'm saying we expect everyone to know every single pitfall of a metric. And therefore, what we wanted to do within the group and a big consortium, we wanted to solve this problem. So we wanted to make sure that we have a metric recommendation framework that can do this job for you. So based on a specific situation that you have, this framework will then be able to tell you which metric you should use in which situation. So this was done with a Delphi process, which is a very useful method in order to get consensus across a large expert consortium. So we had here, we had a small group of coordinators for this process, and we worked on specific concepts of this whole story, like which metrics should we include, and what are pitfalls, what are specific recommendations. And the important part is we had a very big expert panel with a very diverse field of expertises. So not only AI people, but also people from, for example, from clinics, from biology, from statistics. And all of them have their very own view on things. Although we are working, for example, on similar problems than, let's say, people from prediction modeling, we often have a bit of a different way on how to approach things. Not saying that one or the other is better, but it's good to keep these perspectives in mind. And with their iterative feedback, were then be able to derive expert consensus on specific recommendations and ideas of the framework. And this was really a very nice experience for all of us, given these mixed expertises. So, for example, we also had a speech recognition expert in this consortium who is not someone that I, for example, personally work with a lot, which also makes the point of this multidisciplinary collaborations are extremely relevant and are needed in order to make those decisions, to use the knowledge of all of those very smart people. So coming back to how this looks like. So the goal was to have metric recommendations for very specific problems. So what we wanted to do is we wanted to phrase this problem agnostic. So, I'm calling this driving biomedical problem here, but it doesn't really matter if it's a medical problem or whatever kind of imaging problem. What we're saying is, independent of your imaging problem, we will be able to give you a metric recommendation. So we're abstracting from this problem by looking at specific properties of the problem at hand, which we call problem fingerprinting, and I will explain this in a bit more detail. So we're abstracting from the problem that we have. We're asking for specific properties, and based on a specific pool of metrics that we have defined before, we are then able to give recommendations of metrics that you should or should not use in a specific situation. And the core idea, which is really interesting, is based on the pitfalls that we've seen before, because this problem fingerprint that I have mentioned is basically a list of properties that are relevant in terms of metric selection. So for example, I have here put a selection of the fingerprint question. Are we particularly interested in the structure boundaries? If we think of the example with the motorcycles, this is basically the question that we need to ask. If we say yes, we shouldn't use that metric that we have seen before. Do we have small structure sizes? If we think of the brain tumor example, there we said we have this example with the small lesions, and there we shouldn't use the metric that we've seen there. We have class imbalance. If we think of the cancer versus no cancer example, we shouldn't use the accuracy metrics that we've seen before. So this is basically the logic that we have tried to apply. So we analyzed in detail the pitfalls of all of these metrics, and this is also why we put so much effort into analyzing them. And we found that it is a good way to turn this problem around. So basically to avoid pitfalls and think of which metrics can compensate these pitfalls and make sure that we're not falling into these problems in order to make sure that we're using the right metrics. And this whole ended up in a decision tree-like structure for the metric recommendation, which look at first a bit complicated, but we will go through this step by step. So you will find that it's not so complex as it looks like in the first slide. So the main idea is we follow those boxes and those arrows. So we start with the first chunk of the problem. So we first want to identify which is actually the kind of problem that we're using. And you see here that we have 4 different colors of arrows. So these are the 4 problem categories that we're interested in. And these are classification at image level, semantic segmentation, instance segmentation, and object detection. And we've chosen those 4 because they are actually quite similar in the terms of how we evaluate a problem. Because all of them can be somehow interpreted as a classification task at different scales. For example, it could be classification at the image level, at the object level, or the pixel level, which would then be the segmentation tasks. And therefore, they share some similarities in how we validate and how we use metrics, which makes it really nice to put it all into one framework. And also from our analysis, these are the 4 tasks that are the most often used. I mean, obviously, this doesn't tackle every single task that we use in imaging AI, but we are already making a huge chunk of this, which is cool. So the first step is finding out which is the right of these 4 categories, because sometimes the boundaries are not quite clear and it's not straightforward if we should use, for example, a detection or a segmentation task. So we have a specific decision tree on that. I will not go into detail. But the interesting part is we generate what we call the fingerprint that we have seen before. So we go through all of these properties for our specific problem, and we basically say yes for this, no for this, yes for this. So we have basically a list of properties. And then we use that to go to the big part, to the metric selection. And as I said, it looks a bit complex at the beginning, but let's just for now focus on one problem task. So let's say we just focus on semantic segmentation, and then we can already reduce the complexity quite a bit for this decision tree. So we would follow the yellow branch here for semantic segmentation. And then we end up in the first node, which basically says select an overlap-based metric. This means we're looking at a specific family of metrics, the overlap-based metrics. So metrics that basically compare how much overlap do I have between the reference segmentation and my predicted segmentation. So I put them together and compute the overlap. And let's go through this with a specific example. Let's say we want to segment the liver of a CT image, which we have here. So this is the requested output that we want. And we want to identify an overlap-based metric. So we go into another decision tree. So we have many decision trees here based on all the knowledge that we have put together. And we follow the decision tree to make these specific, to get an overlap-based metric candidate. So we follow the decision tree. There are a few inclusion criteria. I will skip that for now, just for the to explain the concept. We will end up in these boxes, which will ask us specific things in the decision tree. So, for example, one question about segmentation is: are we exclusively interested in the center line of the structures? And this could be the case for very thin structures. So, if you think of vessels, for example, which are very thin, or tree-like structures that we see in segmentation, or nerves, or all these things, there it would be really beneficial to look into the center line rather than the full segmentation. In our case, we're looking at a liver, so this is not that interesting to us at the moment. Okay, so we're saying no for this case. So we're going to the next branch here. We follow the no route. Then the next question from the fingerprint would be, do we have an unequal severity of class confusion? This means, are over versus under segmentation equally severe? If we think of the liver example, it's basically not really matter to us if it's more important than we segment a bit more or a bit less of the structure. But there are certain situations where this would matter. For example, if we think of radiotherapy, we want to make sure that we're really that we're meeting all of the healthy tissue, the sick tissue, and that we're not damaging any of the healthy tissue. Or if we want to remove a tumor, we want to make sure that we definitely remove all of the tumor cells. So there are certain situations where this makes a difference. And that's why we are asking all these questions in the decision trees, so that you really think about your problem in order to make the right decision. So in our liver segmentation example, we said, okay, it doesn't really matter. So we're equally handling this. And then we already come to a selection node, which tells us, okay, based on your decisions, these two metrics are the ones that you should choose from. And we specifically made the choice to not end up in final recommendations because we couldn't reflect every single potential use case in imaging AI that is possible. Therefore, we decided, okay, perhaps it's better to have decision trees that help us decide which metrics in my very specific situation should be better in order to make this framework as generalizable as possible and give the last final decision to you. So in this specific case, the decision tree would, based on the decisions that we've made before, basically show us the pros and cons of the different metrics. In this specific case, it would tell us, okay, those two metrics are more or less the same. I could directly compute one by the other. So just pick one of them. It's more or less a preference of community. So we have now selected an overlap-based metric. We would go back to the main overall decision tree. And then it would tell us, okay, select a boundary-based metric. And if we think of the example with the motorcycles that we have seen before, so this would be a metric that can really look into shapes and the boundaries of a segmentation. We would do the same step. We would go into another decision tree, follow the questions of the fingerprint, and then select one of those metrics here. After we've done that, there is the option to also select application-specific metrics. And this is something important that we wanted to emphasize. This framework, of course, is not like the end of the story. There are metrics for specific situations that we perhaps are not aware of or that are very specific for various scenarios of imaging AI. So we wanted to give you the opportunity to include those metrics as well. So, for example, for the liver segmentation example, clinicians are often only interested in, let's say, the more simple things, not the technical details, something like what is the volume of the liver? So we could also include a metric along those regards. And finally, we also give you the opportunity to select metrics that are not based on a reference comparison. So it's not about reference from an expert versus the prediction of the algorithm. So we just give the choice to select something like the runtime of the algorithm, which is important in real-time applications, the carbon footprint, which is obviously getting more important, and those kind of things. And what you've seen now is a main concept of this whole thing, and a big recommendation that we're giving is don't use only a single metric, use multiple metrics, because every single metric has downsides, and we should make sure that we use multiple metrics to compensate the pitfalls and the errors of the others, because there's not this one metric that can measure everything in once. And basically, if you would use other types of problems, if you use a classification or detection task, you would follow the same concept. So you would follow the different branches and you follow the different decision trees for different families of metrics. And in the end, you will have a selection of metrics that are the most suitable for your problem. And finally, we give some small recommendations, which are not the main part of it, but we give some insights on overarching themes like how to report metrics, how to aggregate, how to define global decision thresholds, etc., etc. So this is the overall concept, which is, although I have explained it to you, it's still rather complex. So we tried our best to make it as accessible as possible. So for example, in the biomedical world, we have asked people, so for which specific examples would you like to see recommendations? So what are use cases for which you would like to see those things? So here you see a selection. We have much more in the supplements of the paper, and we've set together with the expert, we have created the fingerprints. And for those specific problems, let's say, I don't know, segmentation of neurons from a fruit fly in microscopy, these are the metrics that we're recommending for those. Or for the liver segmentation, which I've showed you, these are the metrics that we're recommending. So this is something which is nice for the medical community, but something that I think is for, let's say, the more technical people is really interesting, and I use them a lot. What we found throughout the process is that it's the information about one metric is really scattered across resources. So you don't, if you Google accuracy, you won't find all information in one place. You have to go through multiple papers and blogs and whatever. to find all the relevant information. And therefore, we have put together cheat sheets for every metric where you find everything that we found important into one metric. So you find a formula, you find descriptions, some relations to other metrics, multi-class versions, pitfalls, recommendations, all in one place. And from experience, you tend to forget things, and this is has been really helpful, at least for me. Another problem that we have faced is that implementation is really important, and it makes a big difference. So here's one of the pitfalls that we also have in the papers. Depending, in this example for the average precision metric, depending on which implementation and library you use, you will get different results, which is of course concerning. But if you look here at this example, based on how the interpolation is dealt with in this metric, you get quite big performance drops. So for example, here we have a value of 51% versus here a value of 57%. And in many papers, this is already used as we're massively outperforming this method, but it may only be attributed to the implementation. So we've also sat together and made a repository with the standard implementation based on our experiences, how we perceive this as the best implementation. We have also included some educational aspects here, so some tutorials and some warnings, etc., which is currently integrated in the MONAI framework, but it's not part of the overall MONAI. It's just under this umbrella, so you could still use it even if you don't know MONAI or don't use it at all or don't want to use it. So just to make it as easy to use as possible. And the final thing that we have done, and I think this is the most helpful, that we have worked on an online toolkit where you don't have to worry about all these theoretical things. You don't have to worry about the theory and the decision trees. So this online toolkit will guide you through everything. So as you see here, it will ask you the specific questions of the fingerprint. You also have some more explanations. You have some illustration of what we mean by the different questions, because it also may sometimes be not extremely clear. You take your decisions based on your specific problem, independent on what kind of problem it is. It doesn't need to be medical, it doesn't need to be biological, just imaging problems. And then you see at some point the different recommendations popping up. Since we have started this toolkit, we also made some more adjustments. So in the end, you will now get a PDF report where you can see all your choices, which you can, for example, also discuss with your domain experts. We have the metric library where you find all these cheat sheets that I've mentioned. And we're currently working, that's not yet deployed, but we're working internally on something like a metric playground where you can play around with metrics, you see how they behave and learn a bit more about, and get a feeling how these metrics work, which I think is really useful. So I've talked about metrics now a lot. So now that we assume that we know how to choose the best metrics for our problem, does this now mean that we have solved this problem about failing algorithms that look good on paper? And the short answer is no. There are much more things that are relevant. And something else that we have perceived quite a lot is claims of outperformance. And to explain what I mean, when we look at AI papers, what we see very, very often are these results tables here. So if someone wants to present a new method, it's common practice that we compare it to other methods, which makes sense. And the results are often combined in a table where, if you're lucky, you find multiple metrics, ideally the ones that we want to use. And in most of the cases, the proposed method is then somewhat highlighted in boldface numbers. And there's something like, and we're outperforming all the other baseline methods. But that's often end of the story. But this is a big deal because what we see often is we're just seeing point estimates. And here you see an example from the US Food and Drug Administration, who also made quite some comments about that this is a problem. So they mentioned specifically that statistical analysis plays an important role in validating machine learning performance. And that is often underappreciated, and they criticize that there are still publications that present point estimates like we see here without any quantification of uncertainties. And we had the same feeling, and we wanted to get this a bit more quantified, this effect. So what we did is we looked into more than 200 papers here related to segmentation, because that's the most common problem that we're working on in imaging AI. So what we wanted to do is we wanted to know how many of those papers report some kind of variability. And it was quite concerning because more than half of the papers didn't report any kind of variability. And for those who did, it's not better because, for example, there was a single paper that reported a confidence interval and all the others didn't. Some of them reported something that we think would be standard deviation, but in many cases, it's not even specified. You just have the point estimate, then you have a plus minus some other value. But in many cases, it's not even said that this is a standard deviation. And for those who did do that, they didn't specify how standard deviation was reported. Was it for an independent test set? Was it over cross-validation, some other method? And this all makes a difference. And also in terms of interpretation and if it is valid to report this kind of variability. So why is that important? So I mentioned to you that we often see these tables in papers, and such a table, if we don't have variability measures, could mean very different situations. So for example, those two situations here, what you see here, we have 5 algorithms and we plotted the metric values as box and dots plots. So for both of these situations, we would get the same ranking table, although we have very different situations here. So here we could very clearly say, okay, this algorithm is obviously the best compared to all the others. And if we have this situation at the bottom, it's not very clear because all of them are kind of in the same regime. So it's important to somehow graphically show or report some kind of variability or uncertainties in order to make these outperformance claims. So what we did is we looked into those papers and we wanted to know, okay, what is the delta between the proposed method, so the one that is outperforming all the others, and the competitor? So basically, what is the median difference between the first and the second algorithm? And here we use this dissimilarity coefficient metric, which is in my community the most common used metric. And what we found is that the median difference is 0.01. So 1 percentage point in difference is used in all of those papers. And more than 80% of the papers, in addition, claim that they outperform the state of the art by a 1% improvement. And we could already think of, okay, that may be problematic. So we wanted to go into a bit more detail here. So if we consider the median improvement for the proposed method is 1%, the confidence interval the width of the confidence interval should be smaller, because a confidence interval gives us an estimate, how confident am I with my mean estimate. So in order to make this decision, we're outperforming others, the confidence interval should be smaller than the 0.01 improvement. But in reality, what we found is that the confidence interval width is 3 times as large. So we can assume that most of these outperformance claims are not true. So this was our assumption. We went a bit further and we wanted to look into this in a bit more detail. I'm not going to show the details here, but just the results here. We definitely found that outperformance claims are not well substantiated. So we have a high probability that we have false outperformance claims in more than 80% of classification papers and more than half of the segmentation papers. So what you see here in these plots, orange, red means basically bad. So in this situation where it's orange, you probably have false outperformance claims. In green, it's fine. But we also saw that this also depends on the sample size. So the more data you have, the more valid you probably will be in your outperformance claims. But in certain situations, I mean, in Helmholtz, we have all these data sets where we often don't have that large volume. So we often have the problem of small sample size. So on these regimes, we should be very careful how we phrase our reporting. And this is a general problem. Of course, we want to advertise our methods. We want to make sure that we get our papers published. And in many journals, it's a problem if we don't have these comparisons, but we should be a bit careful in how we report it. So we should make sure that we, on the one hand, select the right metrics, and on the other hand, report the results in a proper way. So these are things that are quite relevant. And also for this one, I just realized that I don't have the link here, but we also have an online tool for this one. So if you're interested, I can also post the link in the chat later, where you could insert, let's say you're a reviewer of a paper or you just want to check it for your own paper, you can insert the metric scores of the top performers, give some more information, and then this tool will give you a percentage of false outperformance claims, which is also, I think, quite relevant, especially for reviewers. But as I said, it's not about all metrics and reporting and variability and confidence levels. It's also about data. So in the end, I wanted to give a short overview of data sets, which also is part of the whole story. If I'm not using ideal data sets, then also I can't do specific claims of that my paper, that my AI method is really performing very well. So this is also something that we wanted to look into. And so the problem is that AI researchers typically have. This, of course, depends a bit on communities, but there are certainly communities where there's not that much data available. So in those scenarios, you basically take whatever data you can get, and then you work on that, because that's the only way that we can do it right now. So we work on the data and we produce results, and we often also claim, we can definitely use this algorithm in the real world. But the problem that we wanted to ask is, does it make sense to do it like this way? So are these data sets useful? And specifically what we wanted to look into in this work is, are these data sets fair? And fair, in a sense, is here defined in basically two ways. One thing is, are the data sets representative? So do they really reflect real-world diversity, which is very important in order to make generalization claims. And the second, if we think of the fair data principles, we looked at the A and the R of fair. So is data accessible, legally reusable, and sufficiently documented? So can we use the data that is available, more or less? So what we did is we did a large-scale study here. We looked into AI competitions and more than 400 tasks of AI related to biomedical imaging. And although we have the medical focus again, sorry for that, but I'm pretty sure that this also translates to other fields, and I would be really interested to see if this could be extended. So one thing that we saw here is that we have a substantial bias in the data sets that we see in my community. So if we look at what kind of problems we deal with, so the problem categories here, we have a massive overrepresentation of segmentation. And this is also one of the reasons why you have heard me talking so much about segmentation, because this is just what we work in most of the cases. Also classification and detection, but there are many things that we don't really deal with, although it is definitely important. If we talk about, for example, regression or synthesis tasks, it's not that they are not important, just that we're not used to work on them so much. So here we definitely have the bias. The same also holds true for the body regions. So for biomedical stuff, you obviously work somewhat with the human body. And here, most of the people work with brains. So nearly 30% of people work with brain data. And all the other organs, which are obviously also important, are somewhat underrepresented. And of course, brain tumors is a very severe condition, and it's good that we're working on that. but they are as bad, as important things in other organs that we should also tackle. So another bias here. And what I found, I think, most concerning is if we look at the world map here. So here, what you see is the geographical regions of the data locations. And probably not surprising, and I would be interested also to see if that's the same for other communities. But we have a very big bias towards specific regions, so specifically US, parts of Europe, and China in this case. But there are certain regions of the world map that are completely empty, and we don't really have data, for example, for Africa or South America. And it makes it really hard to assess if we are able to generalize if we don't have any data from these regions. We also found that independent of what kind of bias we have, the way that data is reported is pretty poor in many situations. And we looked into many, many papers, and the reporting of certain things are just not there because people, probably have other priorities in papers, but still things like inter-rater variability, which is really important to assess how good are algorithms. If the reference is very variable, then we cannot really get good conclusions from that. And other things. So we should definitely be more specific in how we report specific things about the data, also enable other authors to understand what we did in our work. And the final thing I wanted to talk about is the accessibility and the licensing of data. Because the way that we currently do it, it really limits how we can use the data. So we had a look into how we can use the data, how it is licensed, and only for 20% we had the feeling, that's fine. And for all the other, there was some kind of uncertainty, inconsistency, or even potential non-compliant stuff. And here we also we talked to, for example, a legal expert who also found the same issues. I don't want to go into detail. I just wanted to show you a few things to raise awareness of how we should think about our data and our licensing. So, for example, there were a few things where we thought, which are kind of at the border. Let's say we're a bit uncertain or gray zone if it's a real problem, but we'd rather consider it as bad practice. As an example, what we saw very often is you have a data set, you put a license, which has very clear terms of how to use the data, but then there's an additional data usage agreement. This often comes into play because we talk to our legal departments, they have specific other things they want to take care of, and then we kind of mix these different agreements together. But if you're the user of the data, it's really not nice to work with this because you don't really know what to do. It's really annoying. You have to deal with all of those terms. It's not really well defined. And in some situations, it may also be that this somewhat contradicts in what the license and the usage agreements are telling you. So you don't really know what to do. And it could be that you get into trouble because you have this uncertain situation. Or something relevant to AI and definitely a legal gray zone is the no derivatives license. Probably have seen that. So this is a license which basically says you're not allowed to use any derivatives of the data or to produce any derivatives of the data. But the term derivative is not so well defined in terms of AI, and it's also legally not clear. It's kind of a gray zone, which is also sometimes updated. If things related to AI, machine learning, training, for example, or data augmentation, is that considered a no derivatives? I don't know. So for those data sets with these licenses, we should be careful to see if we are really able to use that kind of data. Or something, luckily I didn't see that so often, but please don't apply a software license to data. We have seen that in a few situations. Software licenses are not made to use data. And if you use that, it could end up in something like, okay, it does not apply to any data, so it would be basically no rights reserved. We've also seen situations where we definitely see clear inconsistencies. So, for example, being misleading, something like pseudo-open licenses. So, for example, let's say you have an open license. So for example, a license that allows you to use data independent of I don't know if it's commercial or not. But then in order to get the data, you have to go through an approval process by the data owners, which somewhat contradicts the open data policy. So it's really not good practice to have additional barriers to download the data. Or this, other situations where the license was provided, but there's no data for the license, which is, of course, for the user of the data, extremely frustrating to get the data. Yeah, and finally, we had situations which could really, put you into legal trouble, because depending, it could really be that you're not compliant. And one of the most common things that we've seen is that you have conflicting license statements across sources. So let's say you have a data set and you have a website about it, and this website states one license. Then you have a data paper, this states a different license. And perhaps you have, I don't know, is a Nodo where you have even a different license. So as the data user, I really don't know what to do, because I could only do it wrong because of the different licenses. This could really bring the data owner and the data user into legal trouble. Or something that a license is not available at all. You just have a website with a link to the data and you don't know what are the terms of use. If there's no license, it's typically an all rights reserved and you're not allowed to use that license at all. Or sometimes also we really found clear violations of license terms. So things like that you have a share alike clause in the license, which means if you reuse the data, you have to use the same license. This was violated. So what I'm trying to say with this, it's really important to keep these things in mind and to think about it. And I know what I'm talking about today, it's a lot. I mean, we in an ideal world, we all would like to focus on working on our models, but we have to keep in mind that there are more things about data, about AI than just the models. It's about the data, how we make it to work. It's about which metrics we choose. It's about reporting and many other things. It's not straightforward, but it's great to have the community to exchange. And in an ideal world, we hopefully can get to the real goal in the end and make sure that we really measure what we want to have. We want to go to the real goal. And I hope I've showed you a few things that can help you. And thank you a lot for your attention.